All right, physics reaction video number 75. It's been a little while for me. This semester kind of got out of hand, but I'm trying to get back to it here. So did a search for, I think I did a search for Brewster's angle actually, and I found this, so here we go.
Hello, welcome to the third and final part of our unit on wave optics. In this part, we are going to focus on wave effects. So it's a little bit of interference and a little bit of polarization.
Awesome.
To begin, I want to remind you of how light changes when it goes through a medium. So remember, when light goes through a medium, it slows down. So the speed of light in vacuum equals the index of refraction times the velocity in the medium. So I can rewrite the velocity in the medium as the speed of light divided by the index.
So I've talked about this before, and I've talked about how students sometimes want both of those to get on their equation sheet, back when I used to use equation sheets. And it's interesting to me, right? Like, both of these are really, really interesting ways to think about it. They both represent the same thing. This is like, hey, you want to know what's going on in a material, take a couple of things that you can look up, right? This is... if you know this and you can measure this, hey, wow, you can actually calculate the speed of light. I don't know. I think about these as like things you can go into the world and measure, and then what can you get from it. Other people, I think, talk about these. This is just all the relationships, and some people would even write the third one and say the definition of N is C over V. But it's interesting to see, to watch as we sort of do this sort of work for our students. We certainly don't want them stuck in algebra. But it would be interesting to see whether students always sort of pick up on these things the way they're taught, or if they, when they're manipulating them, they think about it in a particular way because it helped them think about or remember it or something.
I can also use that the speed in the medium has to equal the wavelength in the medium times the frequency, and the speed in vacuum has to be the wavelength in vacuum times the frequency. So I can write the wavelength in the medium is the speed in the medium divided by the frequency. But now I can use this formula up here for the speed in the medium. So speed of light divided by n times the frequency. And now I'm going to take this portion and realize that that is the wavelength in vacuum. That allows me to write the wavelength in the medium is the wavelength in vacuum divided by the index of refraction.
Sometimes when I teach this stuff, I ask my students, is n greater than or less than 1? And we've, typically the way it's defined, it's kind of, I guess, always greater than 1. I have to think about that. And sometimes I'll say, look, well, obviously things change. Do you think they get bigger or they get smaller? Well, if you think they get smaller, then I guess you need to slap this in the denominator. But what's hard about this approach is that whereas speed and wavelength change, frequency doesn't. And so if students were to think, okay, well, boy, the frequency has to change too, and I bet you it gets bigger, so I'm going to multiply it by n, that can get you into trouble. Where it's just carefully doing the algebra, you can say, okay, yep, sure enough, the wavelength gets smaller, and we're just leaving f alone here.
If you rearrange this formula, you get the wavelength in vacuum is the index multiplied by the wavelength in the medium, which is 100% analogous to what we had up here, that the speed of light in vacuum is the index times the speed in vacuum, or speed in the medium, sorry. Okay, now,
that was cool.
Moving onward.
I love that, how those were parallel.
Our mission here is to explain why bubbles are colored and why they show this rainbow effect. Why aren't they all blue or all red or all yellow? Why do they shift and change? And that has to do with a phenomenon known as thin film interference.
Just go back for a second here. I think it's such a great motivation, right? So students have seen these effects all the time. And sometimes they associate these effects with just the oddities of how they're in the situation they're in. I mean, bubbles are odd, right? And yet, the way they shimmer, the way they reflect, is relatively straightforward to realize. And of course, what she's going to get to is the fact that the thickness of the soap varies and on a bubble. So how interesting, right? And then you get angle effects, of course, and all the other stuff. I just think this was a really great introduction.
And that has to do with a phenomenon known as thin film interference. For thin film interference, what you have is you have light coming in. Some of that light reflects off the top surface and enters your eye. Some of the light, however, refracts into the medium, is reflected off the next interface, comes back out, and refracts out into your eye as well. Now, these two beams, 1 and 2, can interfere with each other. Now, you might be thinking, well, this is a thin film, so this is really exaggerated here. T is very, very small, so really ray 2 doesn't travel a whole lot further than ray 1, therefore it's not going to be phase shifted a whole lot from phase 1, or from ray 1. And you'd be right, except there's a phase shift that occurs upon reflection in certain circumstances. So when light reflects from a medium having an index of refraction greater than that of the medium in which it is traveling, a 180 degrees phase shift change.
You know, it's funny when she was talking about how it's exaggerated. I was thinking she was going to say something like, "Well, wavelengths are really, really small." But this effect, of course, is one of the dominant effects when it comes to thin films, and so you get this 180 degree phase shift, even if it's infinitesimally thin. And so I'm really interested in how she's really focusing on this. It's super cool.
Or a shift of the wavelength divided by 2 occurs. So now let me explain this statement, because on the surface it doesn't necessarily make sense. So when light reflects from a medium having an index of refraction greater than that of the medium in which it is traveling, so if we are in air and we go into water, so here's my incoming ray, we see that we have it traveling in 1 and it's reflecting off the interface between it n equals 1 and n equals 1.33, so now we've got the first part satisfied. Then the reflected ray has a phase shift. Now I can try to draw sine waves, but we all know how well that works. So instead, I did it this way. So
Nice.
I have my input ray is doing this, and my output ray is now shifted by 180 degrees. So where the input ray was a trough, the output ray is now a peak, and vice versa.
Almost vice
And
versa.
now you can see that even if the film is thin, I have potential destructive interference. We have 2 possible phase shifts occurring at this point. We have a phase shift that occurs because of the mediums we're reflecting off, if we're going from reflecting off a high index material or a lower index material. We also have one due to the thickness of the material. And this can get a little complicated to keep track of. So
No question.
what I have is a simulation.
Excellent.
You can access it at that website. That simulation looks like this. So up here
Cool.
we have our incoming ray. You can see when it enters the medium, the wavelength does shift, as it should. This dotted line is the reflection off the front surface. This, or I guess maybe that one's dashed and this one's dotted. This one is reflected off of the second surface of the film. And then this line down here is the combination of what the dashed and the dotted are doing. And it will show us whether we have constructive interference or destructive interference. Now I'm going to adjust some values. Really,
Cool.
in order to be able to illustrate what happens easily and keep in context with another file I have. So I'm going to change our wavelength down to 500 nanometers. I'm going to let our first medium be air to begin with. I'm going to change the second medium.
So it's really interesting to look at this half wavelength reflection shift, right? So the incoming wave, let me just go back a couple of notches here. 1, 2, 3, 4, 5. Okay, so I'll go back 5 when I come back to this. So here's the incident wave, and it's 0. And then it says that the reflected wave has a half wavelength shift. Well, it kind of looks like an exact copy. It doesn't look like it's been shifted, right? So this is a trough and this is a trough. But the point is that if this were to keep going, it would go up. And yet when this left, it went down. So that's actually super tricky, right? Let's see if that makes sense on the second one here. This one was up and about to head down. And this is, yep, it's about to head down, right? So it'll be interesting to watch. It's time. I'm not sure if she ever changes this one, specifically whether this is a 0 here or not. So let's look and see. So 1, yeah, it seems to be always a 0 here. But at least we can check back here. So now it's coming down, and it was just about to head to its trough. And yep, it's just about to head to its trough. So it's really interesting to think about how to draw all this stuff, which is why it's so cool that she went to the simulation. I lost count, so let me go back one. Okay, so 1, 2, 3, 4, 5 should take us back where I was. So here we go.
From 1.5 to closer to 1.3.
Cool.
Actually, I got it to 1.33 exact. So now I have air, water, and I'm going to change our last, or leave our last index at air. So air, water, air. This is roughly a bubble.
Cool.
Roughly. Okay. Now let's just watch what happens. I've changed the thickness of the film down as small as it will go in the simulation. If I tell it to run, it just animates things.
Oh, very cool.
See how things move. Not really necessary. Oh, I reset everything. Oh, good. My number stayed the same. Having it run is not really necessary to show what we need to see. I do see that the when I reflect off of the front surface, I do get my half wavelength phase shift because I am going from low to high. However, I don't get that from the back surface. And the reason for that is because I'm going from high to low, so I don't get that additional half wavelength shift. However, I do still have a small shift, and that's because of the thickness, and that's what this number here is telling you, that there's a distance shift due to the thickness of the film. All I want to do now is start changing the thickness and watch what happens. So here, I have a thickness of 83, and I get constructive interference. And if I go a little bit thicker,
Cool.
I find a spot at 193 where I get destructive interference.
This is great.
And then constructive again at 2.
What I really like about this, I mean, obviously it's a cool simulation, super useful for the students to play around with too, but I really like how she's just, saying, look, let's start with this particular group of settings, and then I'm just going to move this one. Rather than hitting the run button, I'm just going to slowly walk us through. There's so much here that to just throw it to the students would probably be a problem, but to really, really walk the students through and to have, guide their eye to the things to look at and the things to be able to adjust, then surely you can throw this to the students and say, hey, go have fun. Find me a situation where this color is bright and this color is dim, right? That'd be sort of cool. A cool homework problem on this. Yeah, it's very cool.
288 and destructive again at a thickness of 373, 378, somewhere in there. And then constructive again at 468. And you can see how this is going to go. Constructive, destructive, constructive, destructive. I did this separately for roughly these values.
Cool.
You can see my wavelength is 500, roughly. My two indices for N1 and N3 are roughly 1. For N2, it didn't get it quite to 1.33. I got
Cool.
it to 1.36.
Very cool.
Okay. So close to what we just looked at. And I recorded those values of T that caused constructive and destructive interference. The next thing I did was I calculated what is the wavelength in the medium. So to get the wavelength in medium, I took the wavelength in vacuum and divided by the index of the film, N2. And then lastly, what I did was I took those thicknesses that I
Very
found
cool.
constructive interference, and I divided by the wavelength in the medium. And I took the thicknesses where I found destructive interference, and I divided by the wavelength in the medium.
Very cool.
And if you look closely, you can see a relationship. This is roughly a quarter of the wavelength. This one's 3/4. This is 1 1/4. This is 1 3/4, 2 1/4, 2 3/4. There's a trend. This
I'm just going to pause there, probably stop here. We're far enough in. Man, this was so cool. I really, really, really loved treating the simulation as something you could make measurements on. And I love that, it didn't work out exactly perfect because she just had a little slider. She was just trying to make it be as dim as possible, right? And similarly as bright as possible, or I guess as tall as possible on that graph. Super, super cool. I love also sort of avoiding the angle of incidence problem because this stuff gets much harder as the angle of incidence changes. I just think this was such a great analysis, and frankly, purposely having some little bit wonky numbers and still getting the same results. If you were to go back and change this, anything less than 1.36 would yield the exact same results. The only issue that's probably not built into the simulation is the amount of light that gets reflected, right? Because the difference in index actually determines how much of the light reflects, and she's been focusing on the phase difference. So, if the difference here and the difference here are roughly the same, then the amount of light from the top and bottom is different. But if this were to become 1.34, let's say, the phase difference stuff she was talking about would have been the same, but the amount of reflection would have been way different. So I'm not sure if that simulation has that built in or not. It probably does, actually. Really, really cool. Awesome. All right. Well, everybody, 75th one. That's pretty cool. Hopefully we can keep plugging away and get to at least 100 or something. Remember, have a great day, and physics teachers are awesome.